So today we're going to have a lecture on how to solve the cube with commutators. You're going to be learning basic group theory today. This is how you would solve the cube if we didn't tell you how to use algorithms at all, if you just use math. I guess Matt will teach you all the math you're going to need. A little bit of foreshadowing. From next week on, we're going to be teaching you random things. So we're going to have different stations. If you want to learn things like 2x2, blindfold, big cubes and stuff, we'll have different instructors specializing in different things, and they'll be around the room. So come prepared for that. If you aren't quite up to speed on how to solve the cube yet, we'll also have 1 or 2 instructors doing a review. Are there any questions as of now? No? Okay. I'm going to hand it off to Nan then.
Okay, thank you very much. So my name is Nan Ma, and today I'm going to talk about solving Twisty puzzles using commutators. And let's get started. So I think everybody in this room can solve the Rubik's Cube, hopefully. And this is a great achievement because not many people in the world can solve the Rubik's Cube. But this is only a start of or I would say it's a door to a large world of Twisty puzzles. And let's take a quick tour of this world of Twisty puzzles. There are other puzzles other than Rubik's Cube because if you go to a WCA competition, you can find these kind of puzzles for speedcubing. So these are meant to be solved fast. You have cube with more layers, up to 7x7, and you have more shapes like tetrahedron and dodecahedron. But there are more puzzles than this. Because people have made even more different shapes, like octahedron, it's a face-turning octahedron, or even for cube, we have different cuts. So the regular Rubik's Cube is called face turning because the cuts are parallel to face. You're turning around faces. And for this puzzle, the cut is like this. So it's actually a vertex turning version of a cube. And you can even have different other kind of cuts. Like this one is along the edge, so it's an edge turning cube. It's called helicopter cube. But there are even more puzzles than this. These are all mass-produced puzzles. People have done modification to existing puzzles like Tony Fisher mod this Rubik's Cube into a Fisher's Cube like this. And David Quinn did this kind of mod, and George Bell. So we have different kinds of mods on the existing puzzles. By the way, today we wanted to have David Quinn sitting here. Welcome to Berkeley again. I don't know if Josh Bell is here. Hi. Nice to meet you. So these are mods. They are custom-made puzzles. Some of them has already mass-produced, but some of them not. So if you're buying like this, it's going to be expensive. But there are even more puzzles than this. Because of the recent technology of 3D printing and casting, people have made crazy puzzles. Like this 17 by 17 by 17 is done by 3D printing. And also, it's just countless new puzzles built from scratch. So these are not mods. And and Grant Cohen is here in the audience. Thank you for coming. He's more known for some other things like coding. And so we have seen many puzzles, but there are even more. How come there are even more puzzles? Because if you go to a computer, you can find some simulators. There's a program called Ultimate Magic Cube, where it's very easy. You just choose a platonic solid and choose your cuts, define the depth, and scramble them, you can play. So you can create your own custom-made puzzles by yourself on a computer. And you can play it, and you even have a reset button and undo button, which makes things much easier. And there's a website called Gelatin Brain. On that website, you can find more than 500 of well-defined puzzles, and a lot of them cannot be made on the previous software that I mentioned. And there is even more convenient functions, like you can copy and paste algorithms so that you don't have to remember it. You can just copy and paste, and you can compare time and move counts with other solvers. For example, on this website, I know some friends. For example, Brandon is one of my fellow solvers on this website, and there are some really good speedcubers also solving on this website. For example, Michael Gottlieb was once on the top of the leaderboard. But there are even more puzzles than this. Because you can go to 4D, right? Why are we stuck in 3D? This is the 4D Rubik's Cube. Well, how to look at it? On the traditional Rubik's Cube, it's a 3D. It has 6 faces. Each face is a 2D face, and there are a lot of 2D stickers. And on the 4D cube, you have several different 3D faces, and each little cube here is actually a sticker. So you're looking at a lot of 3D stickers, and some of the stickers are actually associated on the same piece. So other than the geometry, actually the 4D cube is not that different from the 3D cube. And one of the creators, Maria Green, is also in this audience. Welcome. So a lot of people are coming. And
you guys should all come up at the end.
Yeah. And also in 4D, this is like the face-turning version of the 4D cube, and you can also construct different cuts. Like this is the vertex-turning version of the 4D cube. And in 4D, there are more platonic type solids. For example, this 24 cell and this 120 cell. This is huge. It really takes a long time to solve it. And as I know, I think there's only one solver of this one, and only 5 solvers of this one. And it took me like 50 hours to solve this one. But you think of 50 hours, it's like beating the game of Final Fantasy or Legend of Zelda. Well, if you have 50 hours, you can choose to solve this one, or you can beat Zelda, maybe. It's up to you to choose. But there are more puzzles than this. Okay, so this is a 7D cube made by Andrei from Russia. So this is very complicated. And so our slogan is 3D is for species. But there were more puzzles. Let's come back to the plane. I mean, we can have some hexagons hiding the space, forming a tessellation. And each circle here is something you can rotate. So this is a puzzle. And you can solve it. Okay. And you can go to the hyperbolic plane to find the polygon with 7 sides, the heptagons, where you cannot find in the regular Euclidean plane, because I mean you must go to the hyperbolic plane to form this. So if you like the number 7, if you want to solve a puzzle, you should come to the hyperbolic plane to solve it. And there are even more crazy puzzles with complicated topologies. Like this one, it looks like a network with a lot of holes. I don't really understand the theory of this one. Maybe Melinda can give a better lecture on this. And this is the 3D hyperbolic space. Well, it's very complicated. Anyway, so I think I've convinced you that there are many, many millions of twisty puzzles out there. And we have one course, actually 2 courses dedicated for solving the 3x3. So what are we going to do? Should we open the course for each of them? It's impossible. So what we really need is we need to learn to teach ourselves how to solve the Rubik's Cube, how to solve the other puzzles other than the Rubik's Cube. So we need to construct algorithms, and using Commutator is a great way to construct such an algorithms. So let's get really started to talking about the Commutator, because we want to learn how to teach ourselves to solve all kinds of twisty puzzles. Okay, so just set up some notation. Suppose, for any sequence of moves on the Rubik's Cube or other twisty puzzles, let's call it X. I can define the support set of the X. It's defined as the set of the pieces changed by the sequence. For example, the U move, the U-turn, the support is all these pieces. The center is not included because the U-turn doesn't move the center. And X could be a long sequence like this, RU, R prime, U prime. And if you do it, you compare with a soft cube, you can find out that all these pieces are changed. So these pieces are in the support set. So this is the support set. Another term is the commutator. You have two sequences, x and y, and the commutator written as the bracket of x comma y is nothing but x, y, x prime, y prime. So do x and y and undo x and y. So this is the commutator. So how is it useful? Let's start from something easy. Okay, let's talk about trivial fact. The Rubik's cube, UD is equal to DU. It's so trivial. Turn the top side and turn the down side, and anyway, they are equal. And the reason is their support set has no intersection. So if the intersection of the support sets is empty, then you can change the order. So x and y commute. Or another way to say it is the commutator x, y, x prime, y prime changes nothing. Okay, this is trivial, nothing fancy. But the non-trivial thing is that we can add the word almost in the sentence and still work. So if the intersection of the support set is almost empty, then the commutator changes almost nothing. So what does it mean? Let's make it solid by giving some meaning of the word almost. So if the intersection of the support sets is one piece, almost empty, is one piece, then the commutator is changing nothing but three pieces. And these three pieces form a three cycle, meaning that A goes to B, B goes to C, and C goes to A. So this is actually the key theorem of this lecture, if you want a theorem. So that is, if the intersection of the support sets is only one piece, then the commutator is the three cycle. So, and we can use the three cycle to solve the puzzle. And to give a concrete example, let's look at the edge only 3x3. So you can use your 3x3 as a toy, but we only care about the edges to make it simple. Okay, so this is a simulator of an edge only 3x3. Ignoring all the corners. And let's see whether we can find two moves that where the intersection is only one piece. Let's say this is x, moving the front face, x. So this is x. And this is y. Okay? They are symmetrical, x and y. And the intersection is actually only one piece because the support set of x is here, support of y is here. The intersection is the middle piece. And x, y, x prime, y prime, after four moves, we have a three cycle. This piece is yellow, blue. It used to be here, it comes here. This piece goes here, and this piece goes here. So we have a three cycle. Okay, good. So the theorem works. Basically, we verify the theorem. But let's take a closer look at how the three cycle is done. Remember that this piece is actually moving to this direction. Okay? The first move is actually doing nothing but moving this piece to here. So after the first move, this piece has already traveled from this initial position to the final destination. So after that, the latter three moves must be changing nothing. Because the next step the next step y is actually hiding this piece in the safe place so that the third move doesn't affect it, and the last move brings it back. So, in conclusion, this piece actually moved to here due to the first move, and then after that, the latter three moves are doing nothing about it. So what about the middle piece, the piece in the intersection? The first move is hiding it in a safe place, so the second move doesn't affect it, and third move brings it back, so it's back to the original position. And the last move, y prime, is actually moving from here to here. So the middle piece from here is actually moved by the last piece, by the y prime. And for the sake of completeness, let's look at this piece. It's going to this piece, it's going to this position, and let's see how it's done. First move, no change. Second move goes to intersection, and third move goes to that. fourth move. Okay, so we have already seen how the 3 cycle is done. This is a 3 cycle. So actually there are 3 movements in the 3 cycle. The first movement is like a piece is going into the intersection is what X is doing. The second move is the intersection is trying to get out. And this movement is just the opposite of what Y is doing. And the third move has to be this. Actually, this technique is very flexible because every time you can try different ways to define X and Y as long as you remember what X is. Let's try to do something flexible. Maybe we want this piece to go here, this piece to go here, and this piece has to go here to form a 3 cycle. And first thing to choose is, let's say this is the intersection. Okay, then, so which piece is moving into the intersection and this piece is moving up into the intersection? That is the X move, because X move is moving something into the intersection. And the intersection is going here as before, so Y is the opposite of this. So Y is bringing this piece into the intersection, X prime, Y prime, and we're done. So we have a 3 cycle here, here, and here. But, okay, so it's very easy to use commutators to form intersections. But sometimes one of the pieces is just too far away that you cannot really do it. So how do you construct the 3 cycle then? There's a technique called setup. It means that you have a 3 cycle in the middle, and you can choose some setup and undo setup moves in the beginning and at the end to form another 3 cycle with some other configuration. And for example, let's say we want a 3 cycle of this piece, maybe a very far piece, let's say the other side, this edge. So what we're going to do is we'll bring the piece that is very far to something close by, let's say, doing a 180 turn to bring the piece over there to come here. So this move is called setup. So after setting up, we're in a perfect position to do a 3 cycle. We have already learned how to do this. So we do the 3 cycle, and then we have to undo the setup to get it back to the original place. So now we have a 3 cycle of these 2 pieces and the piece that is far away. So actually this is very powerful because you can construct all kinds of different configuration of 3 cycles using this technique. And once you have a 3 cycle, you can construct basically all kinds of other 3 cycles by different setups. All you have to do is just to remember the setup moves so that you can undo it. By the way, this setup, doing something and undo setup is called conjugate in group theory, but the name is not important. Okay, so now we can virtually do almost all 3 cycles. But sometimes you do have the situation that you want to do a 2 cycle. Basically, you are swapping 2 pieces. So how to do it? Actually, well, if you just keep doing 3 cycles, doesn't solve this problem because there is something called parity going on, and the 3 cycle is actually an even parity, and 2 cycle is odd parity. You cannot really add 2 even numbers into odd number. So the way to fix it is actually easy. You just do U like this, and then it will immediately convert a 2 cycle into a 3 cycle. And the reason is also very simple. U is a 4 cycle. It by itself is odd permutation, so it fixes the parity issue. So it's pretty easy to fix, but it has a deep meaning called fixing parity. And what about orientation? Well, you can commute them. Eventually, you have to solve the orientation of the edges. There are several ways to fix orientation. I think the easiest one is just to do 2 opposite 3 cycles to fix the orientation. Let's look at the demo. Let's say we do one permutation for 3 cycles like this. And now we want to eventually get every piece back to the original position, but some of them is flipped. So we want to get this piece back to here, this piece back to here. Basically, we want to undo the 3 cycle. So what if we are undoing the 3 cycle like this? No. This. No, it doesn't work because although we are, I'm completely undoing the 3 cycles. So although they're back into their original position, all the permutations are not changed, so it's not good. Maybe one way to do it is first do a 3 cycle, and then rotate the whole thing, and then undo the 3 cycles. Because this is another way to restore the original position. But now, although they're back into their original position, 2 of them are flipped. So this is exactly what we want. We want to flip the pieces. So we just need to remember what we just did. It's 8 move to fix the orientation, and that's your algorithm. So just do 2 opposite 3 cycles and check the result. And that's your algorithm for fixing orientation. So now, I think we have already got all the tools we need to solve the edge-only 3x3. So the first step is also the key step, is to invent a 3 cycle using commutators by finding xy which has only one piece in the intersection. And for all the other 3 cycles, we can do setup. And for 2 cycles, we can use 1 turn to fix the parity and then solve it using a 3 cycle. And for fixing orientation, you just use 2 opposite 3 cycles. And this is a kind of an easy practice. I recommend it to everybody. Solve it. And after solving all the edges, the cube looks something like this, because you haven't solved the corners yet. But if it's an edge only 3x3, you will be done. So naturally, the next step is to solve the corners if you want to solve the full Rubik's cube. And since all the edges are solved, we don't want to affect the edges anymore. So we need to look for algorithms for the corners. And originally, we talked about these 3 cycles, but this is not a 3 cycle for corners. One thing, it affects corners. And the other thing is the intersection of these 2 support sets has 2 corners rather than 1 corner. So it violates the condition of the theorem. The intersection must have only 1 piece in common. You have 2 corners. So it's not a good algorithm. But we can always do a nested commutator. Because we have this algorithm, this 4-move algorithm. Let's think of the whole thing, the 4-move XX. And the support set is this kind of Y shape. So we were asking whether we can find another sequence called Y, so that the support set has only 1 intersection, and it's actually very easy. We can choose T to be the Y, or you can choose the L or the B. But let's say it's just the B. So this commutator, the whole thing is X, this D is Y, and we can construct a nested commutator. Is in this form, and we need to expand this thing because we need to expand, unravel the commutator. Eventually, we get a sequence like this with 10 moves, and it's a perfectly good 3 cycle of the corners. And if you want to do other kind of 3 cycle, you just need to do setup, and to fix orientation, you just need 2 3 cycles. But yeah, you may think that okay, this is crazy because it's like so long and we're doing this 3 cycle and it's so hard to keep track of everything. But believe me, you have already learned something like this in disguise. For example, I don't know if you're using this A-firm, this 3 cycle, but I use something different but similar than this. Maybe it's a mirror version or different grid. But let's look at what this sequence is, and if I'm the creator of this sequence, what I'm thinking. So if you rewrite this sequence, you will find out that this is actually setup x, y, x prime, y prime, undo setup, where x is D2, where y is R, U, and R prime. So this is in forms of commutator. This is a commutator. So if you're clever enough to choose y to be R, U, R prime, then you're good. But for me, at least, I'm not clever enough to choose y to be R, U, R prime. So let's look at it in some different way. I'm inserting the u prime u here. It doesn't change anything, u prime u. And remember that u and d are exchangeable, so it's okay to change u with d. Now it's like this. And then I can combine this u prime and u with the other bracket, something in the other bracket to form this. So now that in the bracket we have ru, r prime, u prime. Okay, this is a commutator, I know. And this whole thing is a nested commutator, and with setup moves r2 and r prime 2 in the beginning and the end. So this A term is actually nothing but a nested commutator with setup. What I was talking about is nested commutator with setup is nothing crazy. Whenever you are solving the Rubik's cube using this A term, you are using it. And if you are using the nested commutator, you are inventing this kind of algorithm. You are an inventor. So after saying all these things, you need to have a big plan before solving it. What I just told you is like solving the edges, ignoring the corners. Okay, that's the first stage. And the second step is to solve the corners cleanly. This is one valid plan, but there are also other equally good plans, like you can solve them using other like algorithms, because now you're able to construct algorithms. So construct algorithms and fix a plan, find a plan, and that's a algorithm, that's a complete algorithm to solve the Rubik's cube, and you are the inventor of that algorithm. So this is about the Rubik's cube, and since I have time, I would like to talk about another example, just to show you that this method is powerful enough to tackle all the other puzzles. So the puzzle is this. So it's a face-turning octahedron, actually I mentioned in the beginning. It's octahedron and turns in this way. All the 8 faces can be turned in this way. So the first thing to do is to look at how many pieces are there. What are the pieces? This is one piece, it's the edge piece. It has 2 stickers on it. And turns that hole with 2 stickers. And this thing in the middle is a corner piece. It has 4 stickers. This corner piece. And there are some triangles. This triangle, this triangle, this triangle. They're all separate triangles. Each of them has only 1 sticker on it. So there are 3 kinds of pieces. Edge, corner, and triangle. This is important, just to understand how many pieces are there. It's like the Rubik's cube. Rubik's cube has center, edges, and corners, but Rubik's cube, the centers are fixed. And these triangles are moving. So the next step is to try out some commutators. Let's say we can try the commutator of 2 faces that are sharing an edge. I'm talking about like these 2 faces. This is x, this is y, x prime, y prime. So for this kind of thing, the intersection of the support set is the whole edge, including the corners. So let's look at it carefully, closely. What are the pieces that are in the intersection? There is 1 edge piece, there are 2 corners, and there are 4 triangles. Note that although there are so many pieces, there is only 1 edge. So if we are focusing on the edge but ignoring all the other pieces, then the edge is a perfectly fine 3 cycle. But for the corners and triangles, they are complicated. So this is a good algorithm for solving the edge, but messing up all the others. So what about the commutator of 2 faces in some other way, in some other configuration? For example, this green one is x, this yellow one is y. So what if we are doing a commutator of these 2 things? Because the intersection has 1 corner and 2 triangles, we know there's 1 corner, so the corner is doing a 3 cycle. It is nothing about the edge because the edge is not involved in this, and the triangle is complicated. So this is the algorithm to solve the corners. We have 3 types of pieces. We can use the first algorithm. We have the first algorithm to solve the edges, and we have the second algorithm to solve the corners, and we have no algorithm yet to solve the triangles. So this is going to be the plan. This is the first step, this is the second step, the third step is to solve the triangles. And we need to find the algorithm to solve the triangles. And so having nothing to do, having nothing else to try, we need to do the nested commutator. And this is the commutator, this is algorithm number 2. It's the commutator of this space and this space. And the support set is like this. We need to find a move that has only one intersection with this one, and that intersection had better to be a triangle. And so you may come up with a middle layer term. If you can turn the middle layer, then the intersection is only one piece, and this triangle. So it's a perfectly good commutator. X is this thing, and Y is the middle layer term. So that the commutator is the pure 3-cycle of the triangle. And let's try it. So this is X, the 4 move. And now I need to do the Y. It's a middle layer term. Because this simulator doesn't support middle layer turn, what I can do is I can turn the opposite side and reorient the whole thing. And then I do the inverse of X, and then restore, undo the middle layer turn. Okay, I think I did it wrong. Let me do it again. I think it's probably when I'm reorienting the thing. Okay, I've done it. So it seems like I'm swapping this triangle with this triangle, but if you do it again, actually you will find out this is actually a 3-cycle. It's this piece going here, this piece going there, this piece going here. So it's actually a 3-cycle. It's a clean 3-cycle. It doesn't affect the corner and edges, and it's useful to complete our big plan of the third stage. So it's a nested commutator. Okay, so I've done with this example, and as a summary, the first thing to do to a new puzzle, if somebody handed a new puzzle, is of course see how many pieces are there, what type of pieces are there, and then you can use the commutator to invent a 3-cycle. After having a 3-cycle, everything is smooth. To fix orientation, you just need 2 3-cycles opposite to each other. And if you have more than one type of pieces on the puzzle is complicated, then solve it just type by type, like solving the edges first and solve the corners second. And this strategy basically works for almost all the twist puzzles. I think all the puzzles I've shown in the beginning of this lecture can be solved using this kind of technique. And in addition to this, actually every puzzle has its own feature. For example, on some of the puzzles you need to find parity, and there are some other concepts like objects, remotely connected pieces, precision orientation. So there are some other interesting things that you need to learn for all the other puzzles, but you can find out by yourself. And the key thing is really use commutator to construct 3-cycles. After that, basically you're done. So each piece has its own story, and solving it, you are enjoying the joy of that puzzle actually. So for the 42, and now according to the Hall of Fame, there are 141 solvers, and you just learn how to construct algorithms using commutators, and maybe you are the next one for the 40 cube. And that's all for today. Thank you. So any questions? Yeah.
Some example things here about how would you go about solving these?
Okay, these are, I've seen these, I think the gear one is very special, so that the rotation, the permutation is not really a loop, so that this is kind of something that is interesting, but hard to solve by using commutator.
Yeah, there aren't any
What?
There aren't any commutators. If you do APH for speed inverse, you're right back where you started.
Okay. So yeah. So it's like the clock.
Yes.
It's a commutable puzzle. So I think that kind of puzzle is kind of easy. Is it true? Like a clock is kind of it's relatively easier than the Rubik's cube because it's a commutable puzzle.
That's
So
a lot harder than clock.
okay, yeah, I believe in you. But I've never tried it. Yeah, thank you. And this one, I don't know about. Although I have one, I don't know about the math behind this thing. And but it's not very hard to solve. Yeah, I solved it greedily, and I don't know what happens. It will solve. Thank you. So there are some special puzzles that cannot be solved by Commutator, but Commutator is generally a very good thing to solve a very large category of the Twisty puzzles. Yeah.